above a consistent point in space, then what must be true for it to stay there?
It has to match the velocity of the location.
Okay, it's got to track with you. It matches the angular velocity of the Earth. All these are reasonable. Does it make sense that if you're the frame, then you're saying that basically the sum of the forces are zero? That's kind of like where you get that one. Because remember, I thought I did this. Maybe I didn't. I don't know. I can never track anymore. I looked at universal law of gravitation. On one hand, I did force. On the other hand, I did energy. And then when you look at it with respect to force, you get the geosynchronous velocity of the satellite. If you use the universal law of gravitation with respect to energy, then you can find the escape velocity. Remember I did that? Yeah, okay, good. I did that, like 2 columns on one thing up here. So in this case, I'm going to use sum of the forces are 0 because it's not, well, that's not correct. It's orbiting the Earth, so the sum of the forces are mv squared over r. So
It's
then,
not orbiting the Earth, it's orbiting the moon.
whatever. Yes, it is. Yeah, that force is going to be big G, mass of the moon, as Elsa said rightly. She said that rightly, so that's good. Over r plus h squared, yeah, because that's force. And then this is mv squared over r plus h. Yeah. So if you want this thing, the potential or the amount of force, gravitational force that it has at that distance is this. I mean, honestly, do this easier. Just do r and then subtract it when you're done, instead of dealing with this algebraic nightmare, to be honest with you. So let me do that. Clear this out. Just to make life easy, I'll call this D. Okay? And then what we'll get is the altitude is going to be D minus Rm. Okay? And of course, the satellite's mass goes away, and what are we supposed to find? The velocity?
Yeah.
Okay. Yeah, I think so. Yes, I am in fact recording. So then, wait, are we height? Did it say the altitude? Oh, okay. Same position. This is interesting. Oh, the geosynchronous orbit equation is like this, right? Big G m over r.
Can you just do a little research on the internet, find what the
Oh, yeah, okay.
velocity
So
and then do it?
ultimately, actually, okay, if we do this, it's like you'll just come up with, well, no, it doesn't, we don't know V, we don't know R.
You can find me. Look at them all.
We know V, right? Okay, if this satellite is orbiting the moon in a geosynchronous fashion, that means it's moving at the same angular velocity as the moon, right? Which means if the moon turns once every 28 days, see where I'm going with this? That means V is equal to 2 pi d over 28 times 24 times 3600.
3,600 seconds?
Right?
Oh, yes.
Right? Because this is the circumference that this satellite travels through. And this is the amount of time it takes to do that. Here, I can say, so I'll just go ahead and back to this and say D is equal to, oh, yeah, sorry. Yeah. Thanks. So, I think these are both the same, right? They're both the same, because we're talking about the satellite. So that D is going to be equal to big G m the moon over V squared. And then this gibberish has to go down under V squared. Yes. And then of course you get a D minus R to get the answer.
Wait, but doesn't B have D as well? So you have to resolve for it.
Oh, that's annoying. That is correct.
You can't do that.
Damn it. Yeah, so I thought that was going to be a nice, easy thing, but it's not an easy thing. Okay, so as Elsa said, we just have to put this in here. Just have to, that's, yeah. So this is 28 times 24 times 3600. But of course, that part's squared. How do you get the V? So what is, you know the equation, right, that says V is big G M over R. What does that mean? That means at a given radius or given distance from the center of a planet of mass whatever, if I want to stay at that radius, I got to go that fast. Does that make sense? Right? So if I'm the planet and this is the thing that's orbiting me, right? If it wants to stay in orbit there, it has to go this fast. Because if it goes slower, then it's going to degrade and come down. If it goes faster, it's going to go out farther until this radius is met. So that's all this is saying. So then that means this velocity, I mean, look at it. That velocity should be the circumference divided by the time. So I figured that out this way. Now, sadly, that has a D in it, which is a pain in the butt. But then I have to take that D and put it down here. And if you want to be sneaky about this, just do all this stuff as a constant. And then put that in front of the D. Do you know what I mean? Like, let's call it CD. And then square this, do everything out, know that constant, and solve it out in the end. Was that the whole problem? Yes. Woohoo!
I still need to grade my notebook.